respected speaker, faculty members, and participants. It
Recording
is,
in progress.
it is an honor and privilege to welcome you all to this FDP on opportunities and challenges in modern power system, organized by Department of Electrical Engineering, REC Kannauj. We are delighted to have an enthusiastic group of academicians, researchers, and industry professionals joining us for this insightful event. It is my distinct honor to introduce Dr. Anshul Agrawal, sir, Associate Professor and Head of Electrical Engineering Department, BBA, Lucknow. He holds Master of Technology, Gold Medalist in Power Electronics and ASIC Design from Motilal Nehru Institute of Technology, Allahabad. He earned his PhD degree from Motilal Nehru National Institute of Technology, Allahabad. With a teaching experience of more than 13 years, he supervised more than 15 PhD and MTech scholars. He has published more than 130 research articles in the peer referred journals, reputed conferences, and book chapters. He has presented his work in many international conferences. He is a member of various professional bodies such as IEEE, IET, that is Institute of Engineering and Technology, a life member of IST and IAENG, member of organizing committee NIT Delhi, MNIT Allahabad, and NIT Hamirpur. He delivered more than 20 expert talks. Without further delay, let us welcome Dr. Anshul Agrawal, sir, to begin the session. Sir, please, you proceed.
Thanks, Santosh Tripathi ji. So I will share my screen. Just check his screen is visible.
Yes, sir, definitely.
Yeah. So his title is clear, na? Design of power electronics converter for green energy and its control to FPGA. It's visible, na?
Yes, sir. It is visible.
Okay, thank you. So I'm starting my talk. The talk is to designing of this power electronics converter for this green energy and its control through the FPGA. And I will also focus on this application of this converter through the in modern power system also. So there are the few contents which I'm going to discuss. First one is the introduction, then converters. What are the converters? How it can be useful? Basically, we'll going to see this AC to AC converters. Then we'll see the merits associated with the converters. What are the demerits associated with the converters? And how we come to the concept of this frequency converters. What is frequency converter? How it can be useful in concept of power electronics and how it can be applied in modern power systems. This application associated with the frequency converters, how we can control this converter operation, that is we are going to see. After this we are going to see your trigger pulse generation for this converters, and then we switch to the topic of application of power electronics converter in modern power systems. uh, what are the challenges and the future trends associated with the converters application in modern power systems. And next we go to the topic that is your FPGA implementation. Next we come to the topic of power generation through the FPGA, and we will see how FPGA can be used for solar energy, wind energy system, how it can be helpful. With the help of the converter we apply the FPGA. Now next come to the topic of your power converter architecture, and after this we're going to deliver this FPGA based renewable energy application. So these are my few contents related to this today's talk. So introduction. A cycloconverters, as we know, is basically is a AC to AC converter that will convert a AC waveform such as main supply to another AC waveform of a lower frequency. The output we obtain from a cycloconverter is having a frequency less than that of the input line frequency, and it is synthesizing the output waveform without an intermediate DC link. We do not require a DC link, as in case of a rectified inverter system. Now, these are the few merits of the cycle converter. It directly convert a frequency without an intermediate stage. We'll convert simply from AC to AC. It delivers a high quality of sinusoidal waveform that is at a low output frequency. Now, the drawback that is associated with the cycle converter is that the output this obtained is less than that of the input line frequency. If, suppose we are saying that the input is of 50 hertz, the output is 1 by third, means 16.67 hertz. We are getting the input line frequency of the cycle converter. This is one of the drawback of the cycle converter. Now, in order to overcome this drawback, we are now, cycle inverter basically is AC to AC power converter where alternating voltage supply frequency is converted directly to a higher frequency. So you will see there is a single phase auto transformer, and we have seen this dotted line there. These two switches represent these IGBT. One line PC means positive converter. Switch 3 and 4 IGBT switch. This is represent the negative converter, and we are connecting the load. So here basically we are using four IGBT switches, in which four IGBT switches, two represent the positive converter switch and two represent the negative converter switch. 1 and 2 are called as positive converter, and 3 and 4 are called as the negative converter. So this is basically the power circuit of your cyclo inverter. Now, output frequency of the cyclo inverter has a frequency of F naught equal to Fi into Nr, where Nr is termed as an integer and Fi is the source frequency. Now, if we see this waveform, this upper side waveform represents the input supply frequency waveform, and the output voltage waveform is represented by this downside. If we see from, if we take one cycle as 20 millisecond and half of the one cycle is 10 millisecond, so we see this 10 millisecond cycle, they are switch 1 from the positive converter, 2 from the negative converter will operate. Similarly, for this negative half cycle means 10 to 20 millisecond cycle, switch 2 for the positive converter, switch 3 for the negative converter will operate. Again switch 1 4, again switch 2 3. So in this way we are getting the output frequency that is double that of the input line frequency. So here we are getting output that is twice, means if input is 50, we are getting a output as 100 hertz. So this is the idealized waveform of the converter. For the cyclo inverter case, we are getting the output frequency that is higher than that of the input line frequency. Now there is a term called as frequency converter. This frequency converter can be used for high frequency induction heating, where there is a heat to heat the element to a predetermined depth, and depth of this penetration depend upon the frequency of the supply. We are using arc welding and plasma generation also. Recently, converter has also been used as a secondary stage in relatively lower power DC to AC conversion, where voltage step up and down is required. In variable frequency and variable speed and constant frequency output system, we can use this concept of frequency converter, and also we can apply this for renewable energy system, this concept of the frequency converter. Now, if we combine the concept of the cyclo converter and the cyclo inverter, and we get a one circuit that is called as a generalized frequency converter circuit, where we can get the operation in both cases, for cyclo converter case also and for cyclo inverter case also. Means where we are getting the output frequency as lower than that of the input line frequency, and the output frequency that is higher than that of the input line frequency. So if we see this as power circuit, we have four bidirectional switches: switch S1A, S1B, switch S2A, S2B, switch S3A, S3B, and switch S4A and S4B. These are the four bidirectional switches. So, in absence of these switches, common emitter configuration with anti-parallel diode pair is used. The IGBT provide high switching, high current capacity desired for high power applications. So if we see this circuit, we have total four bidirectional switches. 1A and 1B is connected in anti-parallel. 2A anti-parallel 2B, 3 anti-parallel 3B, 4A in anti-parallel with 4B. So this is the power circuit diagram of the frequency converter circuit. Now, if we see this waveform, this is the switching sequence of the IGBT in SPFC, means single phase frequency converter circuit. So if we see this, we on the screen there are three color waveform. First one is the dark red, which we have defined as the fundamental input waveform. Second one is the light green, which we have defined the synthesized output waveform, and third one is the dotted red line, which we defined as the inverted waveform. So if we see this operation up to 20 millisecond cycle, we see half is 10 millisecond cycle. In half, switch S1A, S4A, switch S2A and S3A will be in operation. So you see the output is showing in the green line, which is the double that of the input line frequency. For 10 to 20 millisecond cycles, switch S3B and S2B, and 15 to 24B, S4B and S1B will be in operation. After this, the sequence goes on repeating. So this is the switching sequence of IGBT for the synthesis of your output voltage waveform. Now, after this, we come to the concept of the cycloconverter. If we see this circuit, this is the frequency, generalized frequency converter circuit. So, in order to get a waveform for cycloconverter operation, positive output, for positive input cycle, positive output, switch S1A and S4A in operation. You see this switch, current flow from the switch S1A back to the S4A, back to the source. For negative input cycle, output is positive, input cycle is negative. It means switch S3B and S2B will be in operation. From the source to the S3B, then to the load, then to the S2B will be in conducting mode. So we are getting the output will always be positive for this cycloconverter operation for both positive cycle and as well as for negative input cycle. Similarly, if we see this cycloconverter operation for negative output, we see from positive input cycle, negative output switch S2A and S3A will be in operation. For negative input cycle, negative output switch S4B and S1B will be in operation. So we are seeing that the output will always be negative. For positive input cycle, negative input cycle, output will always be negative. So this we get the cycloconverter operation for negative output. Similarly, we come to the next concept that is called as the cyclo-inverter concept. And if we see this for positive input cycle, positive output, switch S4A and S1A and S4A will be in operation. You see from the source current flowing to the switch S1A, then to the load, then back to the S4A. And for positive input cycle, negative output, switch, you see the switch S2A and S3A. You see the switch S2A and S3A will be in operation. Means switch from source to the switch S2A, then to the load back to the S3A will be in operation. So you see, input cycle is always be positive, but output is positive also and negative also. If we take this as 10 millisecond cycle, so 5 millisecond cycle output is positive. From 5 to 10 millisecond cycle output is negative. So we are getting both positive input cycle output is positive as well as negative. So this is the cyclo inverter operation for positive input cycle. Now, similarly, you will see the cyclo inverter operation for negative input cycle. You see for positive negative input cycle. For negative input cycle, output is positive, means switch S3B and from the source to the 3B back to the load to the S2B will be in operation. For negative input cycle, negative output, switch S4B and S1B will be in operation. You see from the source, current flows to the S4B, then to the load back to the S1B. So you see for negative input cycle, positive output, and we are also getting the negative output. So our input cycle is always be negative. So this represents the cyclo inverter operation for negative input cycle. Now, in order to operate this converter, basically we require the trigger pulses. So to generate the trigger pulses for the proposed frequency converter, we use 6 basic signals. In this 6 basic signal, this signal X3 and X4. First, I will talk signal X3 and X4. This represents the positive cycle square wave as well as the negative cycle square wave of frequency of 50 Hz. Signal X1 and X2 are positive cycle square wave as well as negative cycle square wave frequency NR into F5. Means we are talking about the cyclo inverter operation. Signal X1 and X2 where we demand the output frequency that is higher than that of the input line frequency. Similarly, for the signal X5 and X6, we are getting the output frequency that is Fi by NR. Means we are doing this for the cyclo converter operation where the output frequency is less than that of the input line frequency. So this is represented by the X signal X5 and X6. In overall, it means that signal X1 and X2 represent cyclo inverter. Signal X3 and X4 are the input signal of 50 hertz. Signal X5 and X6 represent the cyclo inverter signal of a frequency higher than that of the input line frequency. Now, next we talk about the gate pulses for different IGBTs. So this, what is the signal we have shown, discussed in the last slide. If you see this representation, X3 and X4 are represent the input signal of 50 hertz, and this is the invert of this 50 hertz. Signal X1 and X2 are represent the signal for required for the cyclo inverter. Means this represents the signal when the output is frequency is higher than that of the input line frequency. And signal X5 and X6 represent the output frequency is lower than that of the input line frequency. Means signal X5 X6 represent the cyclo converter operation. Now, this frequency converter may be realized by using an exclusive OR gate, that is by taking 2-bit input AB from the user. You see these are the two represented by the XOR gate, where A and B are the two inputs. Output is represented by signal Y1 and Y2. Y2 is just the complement of the Y1. So we know that the function of the XOR gate is when both the inputs are high or both the inputs are low. In that case, output Y1 will always be high, and Y2 is just the inverse of the Y1. So in either case, output either of the output is low, or either of the input is low, or either of the input is high. So in that case, output Y1 will be low and Y2 will be high. So this basically frequency converter can be realized with the help of this exclusive OR gate. Now this truth table shows the trigger signal generation for the frequency converter operating in cycloinverter mode as well as in cycloconverter mode. So if you see this cycloinverter operation, you see this what we are doing the signal ending of signal X1 with X3, output line Y1 will be high, means switches S1A and S4A will be in operation. Here what we are doing, ending of signal X2 with X4, output Y1 will be high. What we are doing, switches S2A and S3A will be in operation. In third case, signal X1 is ended with signal X3, output Y1 will be high for cyclo inverter, and what we are doing, switches S2B and S3B will be in operation. When the switch S1B and S4B operation, means ending of signal X2 with X4, output Y1 will be high. Now for the cycloconverter case, X3 is ended with X5, output Y2 will be high. Y2 represent for the cycloconverter case, where the output frequency is lower than that of the input line frequency. What we, in this case, S1A and S4A will be in operation. Means for, if we see this cycloconverter operation, means for negative input cycle, positive output. Switches S2B and S3 will be in operation. Ending of signal X4 with X5, Y2 will be high. For positive input cycle, negative output, switch S2A and S3A will be in operation. Ending of signal X3 with X6, output Y2 will be high. And for the last case, negative input cycle, negative output, switch S1B and S4B in operation. X4 is ended with X6 and Y2 will be high. So this represents the overall trigger signal generation with the help of the truth table, both for the cycloinverter as well as for the cycloconverter cases. Now, this represents the generalized idealized waveform for cycloinverter converter operation, where the output frequency is lower than that of the input line frequency. If you see this waveform, input voltage is of 50 hertz input signal and output voltage frequency is 25 hertz. This means its output frequency is just half of the input line frequency. And if you see this second signal, cycloinverter operation, where input voltage waveform is of 50 hertz, and if you see this output voltage waveform, output voltage waveform is frequency that is double that of the input line frequency. And if we consider input as 50 hertz, output will be of 100 hertz. Means for positive input cycle, we are getting positive output, negative output. For negative input cycle, again, we are getting the positive output and the negative output. This represents the cycloinverter operation. Now, what are the key roles that are associated with your power electronics converter circuits? We are dealing with the energy source integration. We are integrating the sources. We are converting this energy conversion. We are dealing with the power conditioning case also. We are also dealing with the energy store integration, and the scalability and the flexibility is the major key role associated with the power electronics converters. Now, if you see this, as we are doing with wind generator or PV modules or the turbines or the fuel cells, they are the role of the power electronics interface. Either we have to deal with AC or DC, we have to convert this AC to DC into another form of energy that can be used for either for the AC load or the DC load, and we are getting the respective outputs. And these are the energy storage. This is used for the power electronics interface. We are dealing with AC or DC load, and with the help of V controller, we are getting the desired output respective for your required for the signal. Now, the application that is associated with matter power system, that is the renewable energy systems. Either we are dealing with solar energy, either we are dealing with wind energy, or the hydrogen. Hydro. This is the application associated with for modern power system. Either we can use for electric vehicle charging station, we require the DC-DC converter. We can also go with the smart grids. We can go with the high voltage DC transmission system also, and we can improve the power quality with the help of this power electronics converter that can be applied for your modern power system. Now, what are the advantages associated with your power electronics converter? We are getting high efficiency. We also the losses will be low. We are getting the improved power quality. The stability will be high. The compact and the lightweight design, the in mass production will also reduce the cost also, flexible and the scalable for various applications. Either we are going with AC or DC, and enable integration of renewable energy sources. We want to integrate DC, solar energy, wind energy, or hydro energy. We can enable this integration with the help of this power electronics converters. Now, the challenges and the future trends that is associated are the challenges are the thermal management or the cooling. We are going with the initial cost that is to be high, reliability and the durability issue. These are the major few challenges, and the future trends: use of the silicon carbide or germanium nitride, where wide band gap of the semiconductor, with the use of the artificial intelligence and the machine learning in the power system, and the grid interactive or the bidirectional converter that I have already discussed with the help of the frequency converter operating as the bidirectional converters. Now, up to this, we have seen the operation of this power electronics converter, how power electronics converter can be useful in modern power system, how it can be applied, how we can improve the power quality, how the switches can be operated in bidirectional mode. These already we have discussed so much. Now, using PWM in renewable energy control system is not new. Developing the pulse, integrating, generating, and getting the desired output is not new. But the difference, there are many approaches for developing the pulse width modulation technique. But what is interesting is to generate PWM using very high descriptive hardware description language and implementing to this FPGA, that is field programmable gate array. Implementation VHDL allows the targeting of variety of commercial available devices. Then the FPGA can process the information fast, and control architecture can be achieved for space optimized applications. Now, main question arises why there was a need for the FPGA. Now, before this programming logic, we can use a fixed hardware. We have a fixed usability. We cannot alter with the hardware. We cannot. This is a, of a if we design that can be applicable to only for that applications. We cannot alter it. That is its use is limited for that application. Before this, the programming logic. Limited flexibility only is possible by that to adding by software support. That is for the example of processor. Upgradation, alteration, hardware logic was also not guaranteed. An upgrade means when we are doing upgradation means we are designing or we are changing the system. We are going with the completely new system. So this is when they were before this FPGA. Now there's a need arise for this FPGA. With the FPGA, what we can do, we can reprogram our logic reusability. We can use for lower non-recurring energy cost. That is very good for prototyping, and the time is required very less. When we do the programming, we can alter, we can change the programming for various application, and with the help of this VHDL and Verilog, we can change our programming as much time as we want. It can be also act as a testing device for the other digital circuit. It can be economical to be used for the smaller volumes of product, and main thing is that the student can be understand logic design concept in a better way by designing their own custom logic. That can be is a very advantageous for the FPGA. We can design, we can do in lab prototyping, we can design our custom logic with the help of the FPGA. Now there are the few application which I'm showing with the FPGA that is used for the consumer electronics purpose. We are requiring in security system. We also use in video image processing, aerospace also, wireless communication also, medical also, scientific instrument also, and distributed monitoring system. All this application we are using, we are doing with the help of this FPGA. Now, FPGA design tool, there are two important tools that are available in the market. That is your Verilog and the VHDL. Uh, you can do your programming with by adopting any of these tools. VHDL stand for very high integrated circuit hardware descriptive language, and second one is the Verilog. Only difference is just by the syntax. Now, this is the basic picture for the Spartan 3 FPGA kits. If you see this kit, there are lots of inputs and outputs available. Many inputs, many outputs, but there is a one clock frequency that is a 50 megahertz. This you see, this is the 50 megahertz. One clock signal is available, and we have a different A to D converter, D to A converters. You can give your output, you can give your inputs with the help of this IO pins, and you will get the desired output by just programming and applying into your power circuit. Now, before going with this FPGA programming and how it can be useful in the power electronics or by designing the power electronics, how it can be applied in power system, there are few gates which we know already, but I want to discuss how it can be used, designed or how it can be applied with the help of this FPGA. Now, there is one gate that is called as the AND gate. As we all know that the output of the AND gate is only high when all the inputs are high. If any of the input is low or all the inputs are low, the output of the AND gate is low. And the AND gate perform the logical multiplication option, which is most commonly used, known as the AND junction. And the syntax is given as the A ampersand B. Second gate is the OR gate. We know that the output of the OR gate is high only when any of the input is high or all the inputs are high. Then the output of the OR gate will be high. Or otherwise, we can say then when both the inputs are low, inputs are low, the output of the OR gate is low. The OR gate performs the logical addition operation, which is most commonly known as the OR junction. Next gate, we are seeing that the NOT gate. This is the inverter gate. We have, if you remember the slide, we have discussed the one output of the cycle converter is represented by Y1, and Y2 is the output of the cyclo converter, which we applying the NOT gate. The so this simply NOT gate is the just the complement or the inversion. It performs the inversion operation or the complement operation, and the purpose of the inverter is to change the one logic level to at the opposite level. If we have a output as the high, we want to change it at the low, we apply this NOT gate. And when the high level is applied at the top of the inverter, the output level will appear at the output low level or vice versa. This is just the syntax. Why? This syntax is A. This is the NOT gate operation. NOT. Now, next is the NAND gate. We know that the NAND gate output is low only when all the inputs are high, or when any of the inputs is low, the output is high. So the term NAND is derived is the complement or the applying the NOT gate before the AND gate. So this is simply a AND junction with an inverted output. This is the syntax NOT of A ampersand B. In the similar way, we have seen the NOR gate. NOR gate is the output is high only when the inputs are low, or when any of the input is high, the output is low. Or we can say that the just by applying an inversion operation or the complementary operation before the OR gate. So it implies the OR junction with an inverted output. Next comes to the XOR gate. The XOR gate means the output is high only when the inputs are at opposite level. Y X or B. Or XNOR means just by putting an inverted operation before an XOR gate. Means the output is high only when the inputs are at the same level. Now, this is a very simple program, that is a VHDL code for this basic logic gates. And if we see, this is the AND gate operation. How this AND gate is performed, this is the library IEEE standard, which syntax is IEEE.std logic 1164.al. When we enter this entity port, we have defined the two inputs. INA1 is the input, AND gate input. INA2 is also the second AND gate input, and output is stored in OA. That is represent the AND gate output. And we end this entity program. Now we come to the behavior programming. In the behavior, when we write the begin, it means out end of input A1 with input A2 less than equal to output stored in A. We get the desired output in the OA, that is the end of operation input A1 with A2. We will end this behavioral programming. Now, FPGA to control the renewable energy. If we see this block diagram, we have the power source. Power source can be AC or DC. We have a control target, means either we can use converter inverter operation, and we have a load in the form of a AC or DC. Now we are controlling this converter inverter with the help of either by microprocessor, DSPA, or the FPGA. Means we are controlling this gating signal. If we are able to control this gating signal, we can control our operation of the circuit. And this is the A to D, D to A converter. So by this, we can control our renewable energy concept. This is just by showing with the block diagram. Now, FPGA-based variable frequency AC to AC power conversion, AC to AC variable frequency power conversion system can be developed just by making use of a cycloconverter in the new form or AC to AC matrix converter. Undesirable harmonics in the converter can be minimized or can be reduced with the help of this operation. Trigger control circuit can be designed using this field program gate array. We can alter, we can redesign our circuit. An FPGA based system will be developed to generate the trigger pulses for the various switches of the power electronics converter operation. Now, in order for the basic signal generation using an FPGA, in order to generate a basic signal of the FPGA, Spartan 3 FPGA kit is used, whose internal main clock frequency is 50 Hz. Thus, to get a signal at 50 Hz from an input clock of 50 megahertz, what we are doing, we are counting this from 50,000, again reset, and again setting this output pulse. So in order to set or reset this output pulse, the formula used in the code is F out equal to F clock by 2n. F out is the desired output frequency pulse, and F clock is the main clock of the FPA, that is the 50 megahertz clock, and n is the number of clocks to be counted. So we are getting the desired output frequency just by setting and resetting the pulse, and we are getting the desired output frequency. So this is suppose if we need a frequency of output frequency of 150 hertz from a 50 megahertz clock, we are setting and resetting, and we are getting the desired output frequency. So in the next slide, we will show the number of flowchart for the 150 hertz signal generation. So if flag is 1, number of clocks to be 0. Okay, if flag is 1, clock is 0, we are enter into this, and we are setting the clock to be 1. When the clock is 1, we are going inside, and the flag is comes out to be 1. When the flag is 1, either we are casing, we are incrementing it to n into n plus 1, and you are seeing this 1 4 times 6 7 means output frequency. When we are talking of 150 hertz, means 50 megahertz divided by 2n, we are getting the digit as 1667. So one time flag is resetting, again time the flag when is 0 it's setting. So set, reset, we are getting generating the pulse that is of the 150 hertz. So from output frequency f not equal to 1, n equal to 0, flag is, it comes out to be 0. When output is f is 0, n is 0, flag we are setting as 1. So in this way, we are generating this 150 hertz signals. So this is just the flow chart in order to generate 150 hertz signals with the help of this FPGA, 50 megahertz. Now generation of this sinusoidal PWM technique, that triangular carrier wave is generated by using this up-down counter. We have seen this. If you see this sampling process, we are setting this counter to be put in up direction, and then we are going into the down direction. If you see this figure, the carrier frequency FC of the carrier wave is determined by the formula. This is available in the literature. F clock equal to FC 2 to the power q minus 1 multiplied by 2. FC is the carrier frequency, q is the bit size of the up-down counter. Now, if we take as for the 16 bit, if we put as, if you see this, we are getting this sample W-shaped carrier signal. We are setting, we are resetting. We are again setting, we are resetting. And if we compare this carrier wave with the reference wave, we are generating this trigger pulses. This is the sinusoidal sample reference signal. Now, in order to generation of sinusoidal PWM technique, the data value of the sinusoidal reference wave are stored in the lookup table. The binary counter addresses the ROM and the sample of the signal updated by clocking the counter. This is the memory pointer relies on the information to dash to fetch the data from the ROM at an appropriate instant. So if you see this data is stored in the ROM, and by the lookup table, we are addressing this counter and we are setting this pulse. Again, we are setting values are stored at a different memory location T0, T1, T2 up to the Tn. And in this way, we are generating this sinusoidal reference signal. So in this way, we will get this generating the signal by using the memory pointer and the data from the ROM. Now, this is the process of generating this SPW and the digital control. The pulse train is generated at every 0 point of the W-shaped carrier. The memory pointer relies on the information to fetch data from the ROM at appropriate time, and this data is fed to the multiplier unit. Finally, the comparator unit is perform the required SPWM signal. The sample data is stored in the form of lookup table in the internal memory ROM of the FPGA. Now, this is the process of generating this SPWM in the digital control. And if you see this is 0 to 15. We are counting, incrementing the counter from 0, it is going up to 15. Again decremented, again incremented, again decremented, again incremented. And when we compare this carrier signal that is generated by up-down counter with the reference signal, we are generating the PWM pattern. So this is the process of generating the SPWM in the digital control. And the sample data that is stored in the lookup table in the intermemory ROM of the FPGA. So we will now suppose we need to generate a delta modulated wave. So this delta modulated wave is generated by using an 8-bit up-down counter that generates a M-shaped sine waveform that is produced by 8-bit up-down counter. And this formula, that is VR to the power k plus 1 2 q minus 1 upon 10 sine of 2 pi fr 2k plus 1 1 by 2 fr. It is available in the literature. The counter moves up and down values and is stored in the different memory locations by using an lookup table. For a sample sinusoidal reference signal, data representing the magnitude of the sinusoidal need to be calculated by using these equations. Now, if you see this figure, this is the K represent the carrier pulse position, Q is the bit size of the up-down counter, F clock is the clock frequency, FR is the reference frequency. Now, memory pointer relies on the information to fetch data from the ROM at an appropriate instant, and data is fed, and this memory pointer address are stored. Suppose at 000 location, value is 0, at 001, value is 1, at 002, value is 2. We are incrementing up to 15, 0 to 15, again decrementing. So in this way, sine value of different memory location can be generated. Now, this next slide shows your delta modulated trigger signal generation. Delta modulated signal is generated by comparing the scale sinusoidal signal from the lookup table with the triangular curve generated from the up-down counter within the hysteresis band. The samples of the delta model reference wave are stored in the sequential address in the ROM, and binary counter, which acts as memory counter, addresses the ROM, and modulated sample updated by clocking the counter. Switching point of delta model signal can be obtained by the following expression, that is Tn equal to Tn minus 1 plus 2 del x upon P plus 1 to power minus n omega naught Ws cos omega naught Tn minus 1. This formula is available in the literature. You can refer this. Where Tn represent the nth pulse conversion radian, P is the slope of the estimated wave, delta x is the window width, Vs is the maximum voltage of the modulating wave. So this sine wave, within the sine wave, we are generating a triangular hysteresis band wave And when we compare this stresses triangular wave with the sine wave, at the point of intersection, when the magnitude of this sine wave is greater than that of the triangular wave, we are generating the trigger signals. So this shows the generation of delta modulation technique within the hysteresis band, and we are generating the trigger pulses for giving to the operation of the converter. Now, this figure shows the top level schematic diagram in Xilinx FPGA. Now, if you see this PDC represent the phase detector circuit, we have to synchronize the input supply. Input supply is given by X1 and the complement is represented by X2. Now, this dotted portion shown as the personal computer. All this programming can be done with the help of the PC. Now, we will have to generate this code of the reference wave, code of the carrier wave. We have to compare this code with the help of on the FPGA with the help of the comparator, and the output of the comparator is given to the AND gate. What we are doing, we are getting the output of the reference wave, compare them with the carrier wave, and the output is ended with the basic signals. And so, if you remember these, we have discussed 6 signals, X1 to X6. These 6 signals are ended with the reference wave and carrier wave comparator output. And we get the desired signal. And that modulated signal we are given to the power circuit of the frequency converter or to the power circuit of the converter or the inverter. So if we are able to control this modulated signal, we are able to control our operation of the converter inverter circuits. So this shows the controller of the Xilinx FPGA implementation with the help of this top level schematic diagram. Now, RW represent the reference wave generation of the trapezoidal modulation technique. If you see this values, these values are incremented from 0 to up to goes to 15. Then it remains for some duration. It remains to a maximum values of 15. What we are doing, we are in the lookup table. We are storing these values at 000 location, 0 at 0011, 1 at 00112. In the similar way, we will store this value up to the 15. Then after we are getting at 1111, we'll cap this value for some duration, then again decremented to 0, again incremented, again cap for some duration, again decremented. So in this way we are generating the trapezoidal signal. So if you see this trapezoid itself comprises of the two linear segment, namely if you see a slope line is there and a horizontal line. A standard trapezoid signal is generated by using lookup table. The samples of the trapezoidal reference wave are stored at the sequential address in norm in lookup table. Binary counter addresses the norm and the sample are updated by clocking the counter at different memory locations. Now, next slide shows the carrier wave generation for the trapezoidal modulation technique. In order to generate a triangular carrier wave for trapezoidal modulation technique, a Q-bit counter is used. This counter moves up and down value depending on the flag value. If suppose if I set a flag as set as 1, means if we put flag as 1, then counter count in upward direction, otherwise it will count in downward direction. And you see this is the 4-bit counter. It values goes from 0 to up to the 15, then 15 to 0, then again 0 to 15, 15 to 0. So in this way we are generating a digitized triangular carrier waveform by using an up down counter. Now this is the basic flowchart of the triangular carrier waveform. And if you see this flowchart, we'll take as one variable flag that we assign 1. Counter will take as 000. If flag as 1, counter is 0, then we'll put clock equal to 1. If clock is 1, we are putting flag as 1. Now it will goes only and only when clock is 1. And when flag is 1, we are counting in upward direction. In flag is 0, we are counting in downward direction. So you see, when we are getting the maximum value as 1111, counted upward direction. If we are getting a value to 00, we are counting in downward direction. So we'll get as flag as 1111, flag is 0. In other case, flag is 00, FC is 00, flag is 1. So we are counting in downward direction. This is the way to generate a triangular carrier waveform with the help of this up-down counter, 4-bit up-down counter. Now this trapezoidal modulated triggered signal. The trapezoidal pulse width triggering signal is generated by comparing the scale trapezoidal signal from the lookup table and multiply with the triangular carrier waveform using an up-down counter. This is the trapezoidal signal So if we see this triangular carrier signal, this signal this signal is generated by comparing the scale trapezoidal signal. The trapezoidal pulse with modulated syncopating signal generated by comparing the scale trapezoidal signal from the lookup table and multiply with the triangular carrier signal generated from an up-down counter. When we compare this carrier wave with a modulated signal, and when we are comparing this at the point of intersection, when the magnitude of this reference wave modulated signal is greater than that of the carrier wave, we are generating a PWM signal. These are the switching instant pulses for generating this trapezoidal modulated trigger signal by using an up-down counter. So memory pointer addresses the ROM and fetching the ROM, and by using the up-down counter, we are updating the signal. Now, different methodologies for obtaining a different trigger pulses on FPGA can be formulated by making use of reference wave and carrier wave modulation technique. We have seen trapezoidal modulation technique. We have seen that triangular carrier technique. We have seen that a delta modulated technique, which leaves the controller for time-consuming computer tasks of generation and using hardware description language in Xilinx 9.2i WebPack software. Design of control circuit can be done in such a manner that no new component adding for changing the parameter from one value to another. Hardware realization of control circuit and power circuit can be easily done by using an FPGA. The overall system will be compact and no external memory system is required. Tests can be carried out to show the effectiveness and the flexibility of the system. Now, if you see this figure, this represents the architecture of typical power converter system. We see the energy source in the form of DC power bus. We are showing with the inverter. Out of the inverter is improved by using a filter. Finally, we are given to a three-phase system. Then this power inverter circuit can be controlled with this help of this FPGA kit, controller board kit. By controlling this signal, we are controlling this operation of this inverter, and when we are able to control this operation of inverter, we are getting the desired output as per as requirement. So this shows the typical power architecture for a power converter system circuit. Now, if you see this block diagram shows that the FPGA power electronic relation on the FPGA. And if you see this dotted portion, inside this dotted portion, everything is done with the help of this programming. With the help of personal computer, you need one FPGA kit. Externally, what we require is a single phase supply, power circuit, or the load. When we give the supply to the power circuit, and in order to control the power circuit, we should know this programming with the help of the PC. We are able to control the programming. We are generating the signal, trigger pulses, and that trigger pulses we are giving to the power circuit, and finally we are able to control our output load. We are getting the desired output. Phase director are used in order to synchronize the input supply frequency. Now, if you see this FPGA and battery storage using solar cell, this work implement the FPGA based energy system using solar cell under various illumination temperature condition. If you see this block diagram, this represents the FPGA. We are able to control this converter, and converter can be controlled by using this FPGA with the help of this driver circuit. Input as a solar panel, and finally we are giving to the battery. It performs the maximum power point tracking based on P&O method, where it gets the desired maximum power by changing the duty cycle of the switch in the converter. The control algorithm is simple and it is very easy to implement. The algorithm is implemented with the help of the FPGA controller, which control the duty cycle by outputting PWM pulse based on voltage current form of the solar panel. The generated power from the solar cell using a converter is stored in the lead acid battery to supply to the load. Now, FPGA for the wind turbine energy conversion is a ever-growing process, both for environmental personal perspective. When we need to go for the wind turbine, we have to need for the AC to AC converter, which we have discussed already. We have to control the voltage frequency. We have shown the frequency converter operation earlier. Using this less energy will preserve resources to reduce consumer cost, provided appropriate low energy devices made available, reliable put on common place. Successful green power generation requires the more power is produced than consumed in generating the power. The mechanism and control operators develop yield sufficient payback to recapture the overall investment made for the installation and lifetime of maintenance. FPGA technology is currently playing a significant role in energy conservation. Wind turbine control is one of the applications. We have used the PMC module, reconfigure FPGA between energy ventures. FPGA module provide a unique combination well suited for the application requirement, and as we have discussed and seen. This is the simple just a wind turbine model, and this completes my talk. If you have anything, any query, I'm open. Yes. Hello. Hello.
Hello. Yes, sir.
Hi. This completes my talk. If anything, any query, I'm ready to answer.
Yes, sir. Dear
Any
participants,
audience, anybody want to discuss with me? I am available. I am open. Further, you can mail me your query doubt to my mail ID anshul.e@email.bbu.ac.in, and you can take my mail ID from your respective organizers also.
hello, sir. It was very nice talk given by you, sir, based on your design of power electronics converter and green energy, and its control through FPGA. Sir, if anybody wants to ask anything regarding this topic, kindly ask to sir.
Anybody can mail me if they, or anybody can call me. Okay, if you don't want to discuss right now, I'm open.
Okay, sir. Thank you, sir. I suppose no query from participants. If there are any if they have any difficulty, definitely they will send you email, ask the question regarding this topic. Thank you for your valuable time for giving this such a nice talk. Thank you, sir.
Thank you for providing me the platform, and all the best for your FDP. And I hope this FDP program will give you a rich exposure to the participant who are who are listening this all these talks from all these 5 days. And I will again meet in future if anything required from my side. Thanks a lot.
Thank you, sir. Thank you.
Recording stopped.